stability analysis of feedback systems. An important requirement for a control system is that it should be stable. So this means that if a finite size input is applied to the system, the output should also be a finite or a bounded value and not infinite value that go and increase without limit. So stability a system can be defined as stable if every bounded finite value or input produce a bounded output. Okay. So let's say if we follow the impulse input, the system output tends to infinity. As the times tend to infinity, then the system is unstable. So here we have also another statements that we can find in stability in control systems as a critically or marginally stable. So that means that the critically or marginally stable systems normally tends to some finite or values, but non-zero value. Okay. So let's look at these diagrams or these graphs to understand a little bit more the meaning of stability. Okay. Where we have the function respect to time, right? So we have the first function, theta 0 is equal to 2t. Later, the second function is function of theta equal to 5. Another, for example, function of theta equal to exponential minus t, and function of theta equal to exponential t. Okay, so what are the behaviors here in terms of stability? So if we drop this function, right, we have something like this. So that means this is increasing, right, increasing over time. So this system is unstable. Okay. What happened when we draw this one? It's just a constant line. So this one is a stable system, as we can see. What happened when we draw the negative exponential, right? This is stable system. Okay. The last one, because it's a non-negative exponential, so this goes up without limit. So this is unstable. So this is how we have an assessment of stability in with general overview of the function. Well, in this case, the transfer function, right? So let's see what happened when we have or let's see how to evaluate the stability in a control system. So we have a closed loop transfer function okay, as GS. Okay, so we have GS, general transfer function, K multiplied all the polynomial equation, right? And the coefficients. And this continue until we have just the constant, one constant. Okay, this is divided by another polynomial. This is Bn s potential of n minus 1. Plus Bn minus 2 s n minus 2 plus B1s plus B0. Okay, and if the roots of the denominator and numerator are established, has the following equation, right? K is a constant. S plus P1, S plus P2, 1, 2, 3, S plus Pn. If we have it, if we arrange it in this way, so the numerator we call it zeros, and the numerator we call it poles. Okay. And so the roots of the denominator are all the C numbers, so we call it zeros. The roots of the denominator are P from P1 to Pn, and we call it poles. K is a constant that multiply the equation, or normally we call it a gain in the control system, right? So the zeros are values of S for which the transfer function becomes 0, and the poles are the values of S for which the transfer function is infinity or infinite, right? So this is how we break down the transfer function in order to start to analyze the stability. Okay, let's say, for example, we have a function like s minus 2 over s plus 5, right, where the denominator is s minus 2 equal to 0 to start to finding the roots, and then the denominator is s plus 5 equal to 0. So the roots for the first one is s equal to 2, and the roots for the denominator in this case is s equal to minus 5. Okay, so this is the zeros or the 0, and this is the pole. Okay. So the zeros and poles can be real or complex quantities or complex numbers in this case, right? For example, if the denominator is something like let's say s squared minus s6 6s, sorry, plus 8. In order to me to do the factorization or to start to calculate the zeros, so it will be something that it will come like s minus 4, right, multiplying s minus 2. Where for this case specifically the poles are plus 2 that come from the first factor, sorry, plus 4 and plus 2. Okay, so now if we have something like s squared plus 1, if we're trying to calculate the roots, right, the roots will be something like s minus 1, s plus 1, right? But in this case, we will have imaginary numbers. In this case, for we add the imaginary component, and here the poles will be plus 1g and minus 1g. Okay, so this carries us to the next expression that it can be found for poles and zeros, right? Expression that s is equal to the real part plus the imaginary part. Okay, so if we want to have a little more explanation of this, how these two terms is because s squared plus 1, when we equate it to 0, it will be s squared equal to minus 1, and the final root value of s will be the square root of minus 1. That will give you s is equal to minus plus j. And this is why you have the imaginary parts for this equation by itself, for this term. So now just has illustration, right? Let's say we have a transfer function of 2 multiplied by s plus 1 over s plus 1, s plus 2 multiplied by s minus 3. So what are the zeros? What are the poles? Okay, so the zeros for the numerator is minus 1, as we can see, And the poles for the denominator for the first term is equal to -1 for the first one, -2 for the second one, and +2, oh, sorry, +3 for the third one. Okay. Another example, if we have s plus 4 over s squared plus 1s plus 3. For this one, the zero is clear here. The 0 will be equal to -4, and for the poles, in this case, because we cannot factorize just like that immediately, so it's recommended to use the general equation, right? That state that -b plus minus square root of b squared minus 4ac over 2e. So in that way we can calculate the poles that will carry you to -0.5 plus minus j 1.7 approximately. Okay, so I hope you have understanding about the preliminary concepts or the basic information about how to start to work in the analysis of stability, right? So this is the beginning. So finding the poles will finding the poles and finding the zeros will give you an idea. And this is connected also with Rod locus. So when we have the poles and zeros, so we will be able to do a preliminary assessment if the function is stable, like solid stable system, or if it's critically or marginally stable, right? And also if it's unstable, right? So to illustrate this one, Rod locus exemplified how we go about when we plot the poles and zeros in a zero pole plot. So in order to conclude in general form if the system is stable or not stable.